For the longest time, the whole story of AI was just about one thing: scale. Build bigger models, throw more data at them, pile on more parameters. But that's all starting to change. We're hitting this massive inflection point where the entire field is shifting toward a new kind of intelligence, one that doesn't just get bigger, but actually gets smarter. So today, we're opening the codex on that fundamental shift, away from sheer scale and toward deep introspection. And that really gets to the heart of it. The new frontier isn't about just adding more and more layers, the old brute force approach. It's about introspection. We're moving away from what you could call the box world, just making the same old thing bigger, and pushing toward models that can genuinely reason about their own internal processes. And this is what we're calling introspective intelligence. It's a total paradigm shift. We're talking about systems that are built for internal reasoning, for self-correction, and for absolutely radical hardware efficiency. It's about creating AI that can check its own work, validate its own conclusions, and do it all while operating at the very limits of what physics allows. It's about, well, breaking out of the box. All right, so let's open the first chapter and see how this is actually built. We start at the foundation, with the inscription, where these ideas get etched right into the hardware. We're going from the abstract idea of matter to a very precise, new kind of mechanism. Okay, just look at the contrast here. On one side, you got the old way, full precision models. They need a massive scale, and they just burn through memory and energy. But on the other side, we have this new approach, sub-1-bit quantization. And this isn't some small step forward. We're talking about an extreme level of compression that is just ridiculously efficient. And the craziest part? It works on standard hardware you already have. So how in the world is this even possible? Well, the process is kind of like a form of digital alchemy. First, it takes all the complex full precision weights and binarizes them, basically distilling them down to their essence, just ones and zeros. Then, a specialized binary codebook finds all the patterns and redundancies and compresses that data down. And finally, and this is the magic trick, it replaces incredibly expensive computations with the super simple, lightning-fast lookup operation. No special hardware needed. And what's the payoff for all that? Get this, a 20.7 times reduction in memory usage. That is staggering. And that's not a theoretical number, that's a real measured achievement. It's proof that if you rethink the fundamentals, you can get these absolutely massive gains without just building bigger and bigger machines. Okay, so we've seen the mechanism, the physical foundation. But now let's explore its mind. We're moving from the inscription on the hardware to the inner dialogue, how this hyper-efficient system actually reasons. So a core part of this is a technique called the internal monologue. And it's pretty much what it sounds like. The AI has this hidden scratch pad where it basically talks to itself. It generates its own chain of reasoning and then critiques that reasoning, all before it ever gives you a final answer. By doing this, it can catch its own mistakes, which just massively accelerates learning without needing tons of new data. But there's a catch, a big one. It's this fundamental paradox, right? A system that makes a claim can't actually be the one to fully validate that same claim. It can't check its own homework if it has a blind spot. Think about it. If you have a flaw and you look in a mirror, the reflection has the exact same flaw. You can't use the reflection to find the original mistake. In fact, you might just become more confident in the mistake. So how do you solve that paradox? Well, the solution is really elegant. You just separate the act of generation from the act of evaluation. It's called external selection. Instead of having the AI check its work in the same context where it made the potential error, you force it to look at the problem in a fresh context with fresh eyes, so to speak. And the really clever bit is that the same model can do this. You just wipe its memory of the original reasoning, breaking that cycle of error, and suddenly it can spot its own mistakes. Now, this ability to self-validate, to check its own work, that brings us to maybe the most critical piece of this puzzle: trust. So what are the guardian seals? What are the mechanisms that make sure this powerful new way of reasoning is also safe and reliable? The first seal is something called contextual faithfulness, and you can think of it as a mathematical confidence meter. We measure the randomness or entropy in its answers. If the AI is just guessing, its answers are all over the place, that's high entropy. But when you give it solid context and its answers suddenly snap into focus, that massive drop in entropy tells you it's actually relying on the data you gave it. It's a direct, measurable sign of trust. Okay, the second seal is totally different. It's not about measuring something after the fact. It's about building safety right into the model's geometry. It's called vector alignment. See, most safety systems are just a filter you slap on at the end. This goes in and actually modifies the internal wiring of the model itself, making the very decision to answer a question dependent on an internal safety check. And this cathode-anode metaphor is a perfect way to picture it. A good, benign question comes in and you get a clean connection, a spark of knowledge flowing from input to output. Simple. But if a harmful request comes along, the model's internal geometry acts like an invisible force field. It literally deflects the energy. The circuit never completes. And that's huge, because it means safety isn't just an add-on, it's an intrinsic property of the system. All right, so let's pull back. We've got a system that's hyper-efficient, it self-corrects, and it has safety baked into its very core. So, what's it all for? What's the end game? Well, that brings us to the great work, the union of this introspective AI with human discovery. And this is where it gets really practical. This is a framework from the US Department of Energy for the future of science. It's a loop. You design an experiment, you build it, you test it, and you learn from the results. The game changer is putting an introspective AI right at the heart of that cycle. It becomes the intelligent engine, guiding each step, figuring out what hypotheses to test next to learn the most, the fastest. It just accelerates the pace of discovery like nothing else. And let's be clear, this is not some far-off science fiction dream. It is happening right now. What we're seeing is the beginning of a new symbiosis, a fusion of artificial intelligence with the natural world. This is a new engine for solving some of the biggest challenges we face in everything from medicine to materials science. So let's just recap what we've seen inside this codex. We're witnessing the birth of a new generation of AI, one where reasoning is a process, not just a result, where safety is a fundamental geometric property, not just a filter tacked on at the end, where incredible efficiency comes from co-designing the hardware and the software to work together from the very beginning. In the foundation holding it all up, deep transparency, the ability to actually look inside and understand its own confidence and its own reasoning. And that leaves us with one final, very big thought. When our creations can reason for themselves, correct their own mistakes, and earn our trust to this degree, what does that mean for us? The new frontier might not be about making them smarter. The real frontier might be about the questions we ourselves finally have the courage to ask.